Okay, good morning. Let's get started. So we were discussing interpolation of the diffusion coefficient on the faces, right? This is interpolation of gamma on the faces, right? From known values of gamma at cell centroids. Okay. So, we have found that there are two different ways we can calculate the diffusion coefficient on the face, right. One was the arithmetic mean, which was given by what? Gamma f equals or gamma e equals, right. What was the formula we had? We had Fe times gamma p plus 1 minus Fe times gamma e, right. That was the formula we had, and where Fe was delta x e upon 2 del x e, right. That was the length of the arm length, fine. And then we also had this harmonic mean, which was given by gamma east inverse equals what? Fe by gamma e plus 1 minus Fe by gamma p, right, is what we had, right. Gamma e inverse equals so and so, or I could even write gamma e equals so and so to the minus 1, right. So, this is what we have for the harmonic mean. We also had a couple of different formulae through which we have kind of derived this. That was what? That was the QE formula, right, which was given as minus gamma E times phi east minus phi p upon del x e, right. This is one formula we have used in order to arrive at the gamma on the faces, right, by using the correctly modeling the heat flux. Okay. All right. So, that is what we have. Then we have also seen that if we have a condition where, so in the comment section, what we have seen is if we have a thermal conductivity for gamma E is kind of 0, right. Essentially, we have an insulator. Then what we saw was the arithmetic mean kind of retains the effect of both gamma E and gamma p, right. This is the arithmetic mean part, whereas for the harmonic mean, what happens? Gamma E tends to 0, which is what it should be, because you have an insulator, then the heat flux on the face of the insulator should be 0, right. So, that is what kind of recovered by the phase flux. Okay. So, this is recovered correctly by the harmonic mean, but not by the arithmetic mean. Okay. So, let us consider another case where, let us say, the thermal conductivity of the one of the blocks, that is gamma E or gamma p, okay, is much higher than the east. Okay. So, we have a very large thermal conductivity for the p cell when compared to the gamma E. Okay. If we have a case like this, then from the harmonic mean formula, if we go back, so gamma p is much larger than gamma E, right. So, what will happen to this term 1 minus Fe by gamma p? This would tend to 0. As a result, what will be gamma little e? Gamma capital E upon Fe, right. So, that is what we have. So, this is gamma capital E upon Fe. So, essentially there is no dependence of gamma p in this formula, right. It is essentially only depends on gamma capital E, whereas what would have happened for the arithmetic mean? Gamma E would be how much? It would still retain the value of gamma p as well as gamma E, right. So, this will still be gamma E plus gamma p upon 2, okay, or the corresponding one. Now, which of these kind of make sense? So, if we have a thermal conductivity for the p cell very large compared to the east cell, right, what will happen to the temperature drop within the p cell? the thermal conductivity is very large, much larger than E cell. So, we will kind of think that the temperature should kind of remain the same all the way you reach the interface, right. The Tp that we have for the P cell should be the same all the way to the interface, then you should have a decrease in temperature as you go along the E cell, right, which is what the harmonic mean kind of gives you, because it says that because the interface is calculated only from gamma E, right, the temperature Tp that we have. So, the temperature Tp prevails all the way to phase E, right, to the east phase, and from there you have a drop in temperature between E and capital E, right, and this should be dictated by which thermal conductivity, gamma E or gamma P? Gamma E. This should be dictated by gamma E, right, which is the case if you have a harmonic mean. Okay, if you have an arithmetic mean, then it again retains the value of gamma P, which would not kind of give you correct result because you get a different slope, right, wherein the temperature will start decreasing from the P cell to the E cell all the way within the P cell as well. Okay. Now, that means what we are kind of trying to say is if I have, let us say the cells like this, we have, this is my P cell and then this is my east cell. Okay. So, this is essentially we are talking about between these two, and then we also have temperature as Tp, and then it would pretty much remain the same or decrease very little as you reach the interface, and then there will be a drop in temperature as you move within the E cell, right. So, that is what would be captured correctly if you have the harmonic mean. Okay. Now, what about the other consequence? We say that of course, gamma E is not actually equal to gamma on the phase is not equal to gamma capital E, but rather it is divided by little Fe, right. So, we have this factor in here. Now, what is this doing? This is basically accounting for the nominal distance we have to use, okay, between the phase and the capital E. Okay. So, kind of the Fe term, if you look at it, is accounting for the nominal distance. Okay. Now, how is that? How is that the nominal distance? Essentially, if you go back, what is the formula for QE? QE is minus gamma E phi east minus phi P upon del XE, okay. Now, that is what we have. That means, if I were to plug in what is my gamma E, now I have gamma E is gamma capital E upon Fe. So, this will be gamma capital E upon Fe is how much? Delta Xe by 2 del Xe, right. So, this would be delta Xe by 2 del Xe times del Xe, and we have phi east minus phi P. Okay. So, what would this be? You have your del Xe gets cancelled. As a result, what you have is you have minus gamma east, okay, times phi east minus phi P upon delta Xe by 2. Okay. Now, do you see that the harmonic average recovers the correct heat flux, because when we talk about phi east, this is the temperature of the east cell. When we talk about phi P, now this is what? This is the, of course, the temperature of the P cell as well as the temperature of the east phase, right. We are now talking about the temperature drop within the east cell only, right. And what would be the distance between these two? Half of the cell distance, right, that is delta Xe by 2, and then we have the minus gamma E. So, essentially that is nothing but whatever we have drawn here, right. This is Tp, and what is this distance? Delta Xe by 2. Okay. So, essentially you recover the correct heat flux from the harmonic mean. Okay. So, these are kind of the implications, and we have just demonstrated that the harmonic mean gives you physically correct results, because we started off with correct value for the heat flux Q rather than for the looking at what would be the interpolation I have to use for the diffusion coefficient. Okay. So, that is the thing. Of course, we have made several simplifications in deriving this thing. Those are this is a 1D situation, as well as there is no source, right. So, this is a 1D situation, there is no source. What other simplifications we have made? Steady, okay, this was a steady, And I have also made another simplification where there is a jump in the conductivities, right. So, essentially we have a composite material, right. So, essentially this is a composite material which is giving rise to a jump in thermal conductivities across the interface. Okay. Now, of course, these are the assumptions we have made for which the harmonic mean is kind of shown to be performing better than the arithmetic mean. Okay. But in situations where you do not have these things, for example, even if you have a source term, even if your problem is not 1D, even if it is not steady, you have transient problems, and if it is not a composite material, rather you have the thermal conductivity varying continuously within the domain. For all these cases as well, the harmonic mean formula for gamma E outperforms or performs better compared to the arithmetic mean. Okay. Or essentially you get the correct result from gamma E rather than from the gamma E from the harmonic mean rather than from the arithmetic mean. Okay. So, you can use in general, if you want to obtain the diffusion coefficient on the faces, the interpolation by default would be the one is the harmonic average. Okay. That is what you would use unless otherwise stated somewhere, fine. Now, let me kind of complete this discussion by just writing down the 1D equations. Okay. So, those are we have already seen. Essentially, we are trying to solve a steady diffusion equation, that is d by dx gamma d phi dx plus s phi equals 0, and after applying finite volume method, you got A p phi p equals sigma A and b phi and b plus some b. Okay. So, where n b is capital E and capital W, and we have these coefficients, that is A east, A west, and so on. So, A east would contain what? Gamma E A east by del x E, and A west would be gamma west A west by del x W. Okay. Then how do you now model gamma little e, the diffusion coefficient on the east face, as what? Harmonic mean. This is f e upon gamma capital E plus 1 minus f e by gamma p to the inverse, right, where f e is del x e by 2 delta x e. Similarly, what would be gamma w that we get here in the coefficient for A w? This would be, of course, f w upon gamma w plus 1 minus f w upon gamma p to the inverse. Okay. And what would be f little w? This would be delta x w upon 2 delta x w. Okay. Fine. Of course, you can extend it to 2 dimensions and 3 dimensions and so on. Okay. Questions till now? No questions? Okay. Fine. So, essentially you would use the harmonic mean by default. Okay. I may not say that in, let us say, in assignments or in exams or whatever, you would always use the harmonic mean. Okay. All right. So, we kind of take we are trying to now fix up some things which we have not discussed in detail before, right. Interpolation of gamma is one of them, and then a discussion on the linearization of the source term is one more thing, right. I just said that, okay, we are going to linearize, but we did not say how do I linearize it, why do I linearize it, all these things. So, we will come back to that discussion. Before that, I want to kind of discuss on the solution of the linear algebraic equations. Okay. So, we will look at a direct method for solving the equations, and after that we will come back to the discussion on source term linearization, fine, depending on the time, either this class or in the next class, fine. So, let us look at solution of linear algebraic equations. We are again looking at a 1D situation for now. So, we are looking at a 1D situation. Let us say if we have a diffusion equation in 1D, we have already seen how to solve this, the resulting linear algebraic equations, right. How do we solve it? We have already used one method, right. What was that? That was the Gauss-Seidel method, right. So, we have Gauss-Seidel, which is what kind of a method? Is it a direct method or is it an iterative method? It is an iterative method, okay. Essentially works on the guess and correct philosophy. Okay, that is fine. Now, now there is another method which is basically a direct method. Okay, we will kind of try to learn that because we would use that in solving the some more problems that are coming up. Okay, because Gauss-Seidel is kind of slow. If you want to go for 2 dimensions and 3 dimensions, the idea is to use a direct solver that works only in 1 dimensions. Okay, and then interlay this direct solver with Gauss-Seidel in the other dimensions, such that you can still maintain the simplicity of a direct solver in 1 dimension, and you can try to solve 2D and 3D problems relatively quickly. Okay, so that is the idea. So that's why we kind of learn a direct method. This method is based on Gaussian elimination. Okay. Now, what is the difference between Gauss-Seidel and Gaussian elimination? Have you heard of the Gaussian elimination process? I think you have done this in linear algebra. What is Gaussian elimination? What is the philosophy? You have a matrix A, right? I give you a matrix A. What do you do with it? You essentially do row operations, right? And then convert this into, you perform row operations and then convert this into an upper triangular matrix, right? And then you do the row operations on the right hand side also, or no? Do, otherwise you are solving a different problem, right. So, the solution you get will be something else, which is not what ideally correct. Okay. So, then you do the same operations on the B vector as well, on the right hand side as well. You perform the same row operations that you have, and then okay, now we obtained some upper triangular matrix multiplying the. So, you started off with Ax equals B, you did some row operations, right, and then you ended up with what? You ended up with U times x also gets modified? No, right, because it is the same. If it gets modified, then again we are in trouble. X is the same, equals B gets modified to some B star, right, something like that. So, essentially you ended up with Ux equal to B. Now, why did we do this? You can do essentially Ux equal to B has what? Essentially has only one unknown per row, right. So, essentially if you start off with the last row, you have only one unknown, right. You have some equation and you can solve for the unknown, and then you come back to the last but one equation. There you have only one unknown again, because the last one was just solved, and so on, right. So, and then you come back, you essentially do a back substitution and then calculate all the unknowns that you have. Okay. So, this is a direct method. Now, does it sound like a direct method with the application, or does it sound like an iterative method? It is a direct method. We are doing operations, but we are not iterating, right. You are just doing one operation on each of them. You are converting the system, and then you are getting the result in like one go, one shot, right. You perform this on all the rows. Okay, now, this is the basis, and we have 2 operations. One is forward elimination or forward substitution, and the other one is back substitution, okay, converting A to U, and the other one is obtaining x from all these equations. Okay. So, these are the 2 operations that we have. Now, for the equations that we get from the finite volume method, okay, at least for the diffusion equation, all the equations are kind of have a nice pattern, right. What was the pattern? These coefficients align along the diagonal. So, there is these are kind of banded, and also it is a sparse matrix, right. All these things are there. So, essentially we can apply Gaussian elimination, and Gaussian elimination kind of gets simplified into a very convenient algorithm, okay, known as Thomas algorithm, or also known as TDMA, which stands for what? Tridiagonal matrix algorithm, which you know already. Okay. Tridiagonal matrix algorithm. Why is it tridiagonal? Because on these diagonals the coefficients are non-zero, that is all. Okay. Okay, so now we are going to look at tridiagonal matrix algorithm, which is a direct method to solve a 1D set of equations, right. Essentially we have these equations. Now in order to kind of conveniently present these this algorithm, we are going to do some modification to the set of equations we get. Okay. So what was the equation set we always intend to solve? We always intend to solve or get it in terms of AP phi P equals A east phi east. I am considering a 1D situation, A west phi west plus some B, right. This is the equation we usually work with in this particular finite volume method, whereas to present a direct method, I am going to kind of rewrite this equation, which is one equation per one cell, into slightly differently using the index notation. Okay. Not actually index notation, using an index I. Okay. So this is basically AI. Let me use the term Ti, or essentially phi P stands for, let me put back, yeah, I mean, so essentially this is phi is T, okay, T equals phi, we are solving for temperature or some phi. AI Ti equals Bi Ti plus 1 plus Ci Ti minus 1 minus Ti minus 1 plus some Di. Now, are these two equations the same? They are the same, because east is nothing but I plus 1, west is nothing but I minus 1. Okay. Fine. So, we have AI Ti, I is nothing but your P cell, right. AI Ti equals Bi Ti plus 1 plus Ci Ti minus 1 plus Di. Now, we have to also decide on what are these I notation. Okay. Essentially, what would be the boundary, what would be the interior cells. So, for that let me say that I equals goes from 1 to all the way to n minus 1 to n, okay, where 2 to n minus 1 constitute the interior cells, okay, and 1 and n constitute the boundary cells. Okay. Boundary cells, I mean the boundary condition itself. Okay. So, that means 2 is itself is a boundary cell, because it is sharing a one face with a boundary. Okay. Fine. So, essentially 1 and n is where we apply the boundary condition, 2 to n minus 1 is the unknowns that we have to solve for. Okay. All right. So, then what we do is, let us say if I have a Dirichlet boundary condition. So, for example, if I have a Dirichlet boundary condition for temperature, I would say T1 is known, right. I would say T1 is some constant. Now, if T1 is constant, what would how can I rewrite this equation in a matrix form to, so what would the coefficients be if I have to say T1 is known? This would reduce to A1 equals 1, right. What would be B1? B1 should be 0, because T1 is already known, B1 is 0. What would be C1? 0, because we do not have a cell where T0 is there, right. What would be D1? D1 should be T1, right. Essentially your matrix is like 1 times the unknown equals T1. So, unknown gets equal to T1, okay. That is kind of very trivial. So, this is trivial. So, the coefficients get modified like this if you have a Dirichlet boundary condition, and it gets modified differently if you have a Neumann boundary condition. Okay. Now, again, as we have seen that 1 and n are the boundaries itself, we do not have 0 and n plus 1 cells, right. So, we do not have, so any variable that is referring to 0 and n plus 1 does not physically exist, right. So, essentially what does that mean? That means that I can set, because we do not have Ti minus 1, if I am writing an equation for I equals 1, right, because this will be 0, that means what would be the coefficient? The coefficient would be C1. C1 would be always 0, because it tries to connect to the T0, which is physically not there. So, okay, this is irrespective of whether I have a Dirichlet boundary condition or a Neumann boundary condition. Okay. C1 is always 0. What is the other one that will be 0 if you go to the other end? Bi, I equals n, right. You are trying to write an equation for nth cell and you do not have a connection to n plus 1. right, because you do not have anything outside the boundary for that. So, essentially Bn is also equal to 0. Okay. So, these are set to 0, so that the connections to the outside the boundary are disconnected. Okay. Fine, these are always 0 irrespective of the boundary condition we apply. Okay. Now, if this is the case, what will be an equation for, so we say T1 equal, T1 is known. So, T1 is known. What would be an equation for I equals 2? I want you to just plug in I equals 2 in equation 1, that is all. What will that be? A2 T2 equals, A2 T2 equals what on the right hand side? B2 T3, okay, B2 T3 plus C2 T1 plus some D1. Out of this, what are unknowns? T2 an unknown, okay, what else? T3? T3 is an unknown, oh this should be D2, I am sorry, okay, thank you. This should be D2, okay, should be with black, okay. What are the unknowns? T2 is an unknown, T3 is an unknown as well. What about T1? Known. So, where will you send this term? To the right hand side, right, it is known. So, this is known. D2 is known or unknown? D2 will have what terms? Source terms, right, depending on source. This will actually all the known terms. This is actually the B term that we got in our original equation, right. So, this is known or not known? Known, this is known of course. Okay. So, all these things are known. So, I can write an equation for cell 2 as, so essentially T2 is now a function of, other than the constants, what is it a function of? The unknowns, T3 and plus some constants, right, we have this. Now, can we repeat the same process for cell T3? If you write I equals 3, you will get something here, A3 T3 equals B3 T4 plus C3 T3 plus D3. Do you get this? T2, okay. So, this should be T2, is this correct? I equals 3, same thing, okay. In this, what will be T3 a function of? T4 and T2, T2 is now what? It is a function of T3 again, right. So, essentially that T3 can be sent to the left hand side. So, then T3 will be a function of what? Only T4, T4 and constants, right. Is that correct what I am saying? Do you see? For cell 2, T2 is a function of T3, for cell 3, T3 is a function of T4, right, and so on. That means, we have some kind of a forward dependency for each of the cells. Okay. Then if I continue this, what would be Tn a function of? Tn plus 1 and some constants, but do we have Tn plus 1? Because we have already set Bn equal to 0. So, then what will be Tn? You actually get the value of Tn at this stage, right. So, this step gives you what? Value of Tn, right. So, essentially you obtain value of Tn from this equation, right. Tn is obtained, okay. Now, once you have Tn, can you use the previous equation would read Tn minus 1 is a function of Tn and constants, right. Now, can I use this equation and calculate Tn minus 1? I can. So, essentially we can start the back substitution, right. We have now what we have done is a forward elimination, now I am doing a back substitution, right. I would use this equation, calculate Tn minus 1 and use the previous equation Tn minus 2 and calculate Tn minus 2 from Tn minus 1 and so on, and eventually calculate what? T2 from T3, and T1 is already known, right, it will anyway go. So, that is the back substitution. Okay. In the previous stage we have done the forward substitution, now we have done the back substitution. Okay. Do you see the essence of the algorithm, of the triangular matrix algorithm or Thomas algorithm, right. We are essentially doing the row operations, but in a different way, right. This is nothing but the row operations. Like for every cell we have a dependency on the previous cell, and you keep doing that. When you reach the last point, because of the boundary condition, you actually get a value for the unknown, use the value of the unknown and then trace back using the same equations and you will get all the unknowns, right. That is all we have done. Okay, very good. Now, let us actually come up with an algorithm. Okay, now we have talked about the philosophy. Questions till now? Any questions? Yeah. T1 is not at the cell, so T1 is on the face of the cell, right. So, essentially between the distance between the T1 and T2 is what? Delta x e by 2. That will again get counted in the coefficients, right. Now, can you use this algorithm for finite difference? You can use, right. You can use the same solution technique or finite element, anything, right. Other questions? Yes, right. Okay, the question is how do you calculate the flux on the boundary faces, on the east and west faces for the boundaries? We have used a one dimensional formula, right. For example, on the let us say gamma A, let us call the east, so the west is A, okay, this is the first cell, right. How do we calculate gamma A? Let us say gamma A is basically this phase, right, and then this is your first cell P, right. We would use this value phi B and the phi P and this distance delta x B and calculate it, right. You would use a one sided formula, right. That is all, kind of a forward formula for the phase gamma A, not actually gamma A, this is basically your flux. So, what I am talking about is minus gamma A partial phi partial x at A, right. You would use a minus gamma A times phi P minus phi B by delta x B, right. This is how you would calculate. Gamma A now can be calculated, so you need a kind of a ghost cell or something, right, or because now we do not have a value, you could even use gamma A equals gamma P, right, because assuming that you do not have anything on the other side, right. Essentially you are using a harmonic mean or arithmetic mean and you assume that there is a same material on the other side, right. So, what if you use a kind of a virtual cell, what will be the value of phi? That is basically same as whatever interpolation you want to use, right. If you assume that you have the same material on the other side, then you can use gamma A as this thing. Now, if you have, okay, that is a good question. Now, how do I calculate gamma on a boundary face, right? Let us say I have a insulated boundary condition, I say Q is 0, right. Now, what will be gamma A? You do not need to calculate, right, because Q is 0, gamma partial T partial x would always turn out to be 0, that is all, right. Now, if it is not the case, then you have to assume that there is a material on the other side, that will be usually given, because that will form because the gamma values are, the problem only is that the gamma values have to be interpolated in the interior of the cell faces, right, but not on the boundaries, because that will be part of a boundary condition. So, that will usually be given, okay. We will come back to that if there are other questions on that. More questions? No? Clear? The philosophy is clear? Why we are going through the forward substitution and the back substitution, right? Sorry? Yes. Okay. Okay. Yeah. Okay, the question is how to find out the source term, how to satisfy conservation for the first cell. Now, the source is unknown or known? Source is known, right? Okay, so essentially you want me to solve the assignment here. So, okay, so as far as the assignment is concerned, how do you calculate, so where do you write the source for? For which point? For the cell centroid, that is all. So, when you write an equation for the first cell, you would use the xp or whatever as what? Delta x e by 2, that is all, right. Other questions? No? Okay, fine. Then let us move on with the algorithm. So, we are looking at TDMA. Okay. So, what is that that we are trying to do? We are trying to do for every Ti or phi I, for every Ti we are kind of seeking a relation in terms of Ti plus 1, right. That is what we are seeking. So, essentially that means we are seeking, if I have Ti, I am seeking a relation for Pi Ti plus 1 plus Qi, right, where Pi and Qi are some constants that depend on the particular cell, right. This is basically the functional dependency. We have just written that Ti is a function of Ti plus 1 comma some constants, right. This is what we have written till now. We said T2 is a function of T3, T3 is a function of T4 and so on. So, that means this is what we are seeking, right. So, we seek a relation that looks like this. Ti would be some factor Pi times Ti plus 1 plus Qi, right, that is what we want. And then after after having just obtained Ti minus 1, okay, what would be Ti minus 1? So, the previous one would be Ti minus 1, that would be how much? Pi minus 1 Ti plus Qi minus 1. Is that correct? Essentially P and Q are now tied to the cell, right, and right hand side the unknown should be one cell forward to the previous cell, right. Essentially Ti minus 1 is Pi times Pi minus 1 times Ti plus Qi minus 1, okay. So, let me write down the original equation. Original equation was what? We had Ai Ti equals Bi Ti plus 1 plus Ci Ti minus 1 plus Di, right. This is the equation we have. Let us call this as equation A, okay. Let us call this as equation B. Let us call this as equation C, okay. A, B, C, D, are they known? They are known from the discretization, right. They have these A east, A west, A north, whatever, right, all those things. But there is one catch here. What would be the difference between Bi? Well, in this case there is no catch, isn't it, because we always wrote A east, phi east equals A, A phi times east and west. So, there is no problem here, okay. I will come back to that question later, fine. So, now what I want to do is I want to kind of substitute for Ti minus 1, okay, for this value into the equation for A, right. I want to substitute Ti minus 1 into this equation, fine. Can I do that? Okay. So, I would substitute Ai Ti equals Bi Ti plus 1 plus Ci times what is Ti minus 1? Ti minus 1 is this entire expression Pi minus 1 Ti plus Qi minus 1. So, I plug in here, this would be Ci times Pi minus 1 Ti plus Qi minus 1 plus Di, okay. Essentially we substituted equation C into equation A for Ti minus 1, right, that is all we did. Now, why did we do that? Because this final equation we got is a function of what dependent quantities? Ti and Ti plus 1 only, right, okay. So, that means if I go forward, if I simplify this thing, what will be the coefficients for Ti? Ai and Ci Pi minus 1 minus Ci Pi minus 1, is that correct? Equals, what will be the coefficients for Ti plus 1? Bi, that is all, okay. And then what else the constants? Ci times Qi minus 1 plus Di, okay. So, this is the constant, okay. Then can I write it as Ti equals Ti plus 1 times Bi upon Ai minus Ci Pi minus 1 plus Di plus Ci Qi minus 1 upon Ai minus Ci Pi minus 1. Is that fine? I just divided the coefficient of Ti for all the terms on the right hand side, fine. Now, can we compare this equation which is, let us call it as D with B? Can we compare D with B and obtain the coefficients? Right now, on the left hand side you have Ti here you have Ti, this is Ti plus 1, this is Ti plus 1. So, this coefficient Pi should be equal to this coefficient and Qi should be equal to the constant here, okay. So, if I compare, can you help me write what is Pi? Pi is Bi upon Ai minus Ci Pi minus 1, okay. And then what would be Qi? Di plus Ci Qi minus 1 upon Ai minus Ci Pi minus 1. Okay. Okay, now these are the recurrence relations for Pi and Qi, because Pi Qi now depend on what? Pi minus 1 and Qi minus 1. Okay, so because it's kind of a recurring relation, only if you know Qi minus 1, Pi minus 1, you can obtain Pi Qi and so on, right. So this is nothing but the forward elimination or forward substitution. We are calculating what is Pi Qi from Pi minus 1 and Qi minus 1. Okay, so that is the forward substitution that we are doing. Okay, because Pi is now depends on Pi minus 1 and Qi depends on Qi minus 1 and Pi minus 1. Okay, so these are the recurrence relations. Fine. So let us now, but we have to start off with somewhere. So where do you start the forward substitution? With what cell? First cell. Okay, let's say 1. So if you say I equals 1, what would be P1? So what is the conditions we had on the B and C? We had two conditions. What was those? C1 is 0 and Bn we have set it to 0. This is to kind of disconnect the T0 and Tn plus 1, okay, but this has nothing to do with the boundary conditions. Okay. So now what will be Pi if you plug in I equals 1? Will there be some B1? B1 upon A1, because C1 is 0, so this will be B1 by A1. What will be Q1? C1 is 0, so essentially this term is 0, this term is 0, D1 by A1, D1 by A1, right. So we can start off with P1 and Q1. PQ are the new unknowns we have introduced. We said we have to seek a relation that looks like Ti relates to Ti plus 1, right. That is how we introduced P and Q. But where do we get these values P and Q? They have to come from the discretization, which is nothing but the A east, A west and so on, which in this particular notation are nothing but A, B, C, D, right. So we have obtained P1, Q1. Now can we use these recurrence relations that we have to obtain P2, Q2 once we have P1, Q1? Okay, let us see. What will be P2 from the equation? B2 by A2 minus C2 P1. Now is B2, A2, C2 known? Yes, they are known as soon as you finish the discretization. P1 is just now calculated from B1, A1. What will be Q2? D2 plus C2 Q1 upon A1 minus, A2 minus C2 P1. Now is D2, A2, C2 known? Known, right, for the cell 2. What about Q1 and P1? Known, we have just calculated them. So P2, Q2 can be calculated, right. And then we keep calculating P3, Q3 and so on to where? P and Qn, right. P and Qn. What is Pn? 0. Pn is 0. Why is it 0? Because Bn is 0. Pn is 0. Can you calculate Qn? It will be some Dn plus Cn, Qn minus 1 upon An minus Cn Pn minus 1. It can be calculated, right. This is essentially Dn plus Cn Qn minus 1 upon An minus Cn Pn minus 1. Okay. So this can be calculated. Pn is 0. Fine. Now if my Pn is 0 and Qn is some number which we calculate, some value, then if we go back to the equation, the original equation, okay, if we go back to the equation B, okay, which is nothing but, so if I plug in this equation I equals n, what will this be? Tn equals Pn times Tn plus 1, of course Tn plus 1 does not have any meaning, plus Qn. What is Pn anyway? We got this as 0. We got this as 0 because we have set Bn equal to 0 to begin with. We have disconnected the connection, like we have kind of disconnected these outer cells, isn't it? So that is Pn is 0. What about Qn? Qn, do we have a value for Qn? We just calculated Qn. Then what is Tn? Tn equals Qn. So you can calculate Qn and you get the value for Tn. So this is your first calculation, right, of the back substitution process. So Tn is now Bn, Okay. So, what we have is you calculate Tn equals Qn, you set this thing, Qn is known, calculate Tn from here. Then we go back to our original equation, which was Ti equals Pi Ti plus 1 plus Qi, right. This is our original equation. Now, at this moment, do we know Pi Qi for 1 to n? All the values? We know, right. So, essentially Pi Qi for I equals 1 to all the way to n are all known, right. Now, what is that we calculate? We just calculate what is Tn, right. Now, can I calculate Tn minus 1 from this equation? I just plug in I equal to n minus 1, calculate Tn minus 1, next I can calculate Tn minus 2 and so on, calculate T2, right. That is your back substitution process. So, use this relation for I equals n minus 1, n minus 2 all the way to 2 and calculate Tn minus 1, Tn minus 2 and T2, fine. That is the Thomas algorithm, that is all. We started off with forward substitution, that is nothing but calculation of the new coefficients P and Q, and we have used the same reconciliation. Once you find the final temperature, you come back and calculate in a back substitution, calculate Tn minus 1 to T2. Okay. Now, this works both for Dirichlet or Neumann. Okay. We have not discussed that, only as a special case I discussed, but it works for both. Have you heard of LU decomposition? Also, yeah, how is it different from Gaussian elimination? Product of matrices, okay. Is it different from Gaussian elimination? It is not different. It is just storing it. Essentially, LU is the same as Gaussian elimination, right. Instead, we are just storing it as two different matrices. Why do we do that? Is there an advantage of storing that? Multiples. Essentially, if your right hand side changes, you can still use the same system and then solve it, right. The coefficients are the same, right hand side is different. That means the same problem with different boundary conditions, you can still use the same coefficients, right, and then calculate. So, that is why we are storing it. Now, is this different from LU or Gaussian elimination? It is not. What we have done basically is a kind of LU decomposition for a tridiagonal matrix, right. That is Gaussian elimination applied to tridiagonal matrix, that is all. Do you see that? Okay. Now, this is a direct method which you do not have to worry, because you will all code this in one of your assignments, in the upcoming assignment, right, and then you can see for yourself that this direct method would be much faster than the iterative method, that is the Gauss Seidel. Okay. Now, can we extend this to 2 dimensions, this process? We can, right. It is just little more complicated, right. Instead of tridiagonal, you will get maybe pentadiagonal. So, then we can do that, which we will not do. Rather, what we do is we kind of look at a different method, which is basically combines the Gaussian elimination with the direct solver, that is tridiagonal matrix algorithm, such that you do not have to write a much complicated 2D solver as such. Okay. We will kind of use this in the coming lectures, fine.